Welcome to the new Grassmann.jl computational language paradigm. I am Michael, and I am the creator of the Grassmann.jl language design. And today we're going to be demonstrating some usage of this package. So using Grassmann, and all of these packages have been built from the ground up with the geometric algebra computational language paradigm in mind. And I'll only be using Mackie for visualization after my calculations have been done to aid with the display of the results. And so I've created this new I've been playing around for several years now with this computational language design using geometric algebra based on the Grassmann.jl language design. And so all of these calculations that I'm going to be demonstrating, I've been maintaining the capability to do for over 4 years or 5 years now, or even longer, depending on what it is. But I've been changing around how the calculations fit into the Grassmann.jl foundation. And now I like to start out with something called a TensorField now as well. So if I define this parameter t, which is from 0 to 2 pi, so in Julia this is just a typical abstract range, and I've created a TensorField of it. That means that this is now just a parameter that I can use to do geometric algebra with. So for example, we can generate the two-dimensional basis here, and then we can do something like exp v2 times t, and that produces a new tensor field where if we plot the result, it's a circle now, because this is from the parameter from 0 to 2 pi, and the tensor field contains enough information to be able to plot the circle basically. And we can, and this is like this tensor field is like an algebraic object that can numerically be used to compute different things, as we'll see. For example, we can sum together two of these, and now it looks like a spiral. So what we see here is that the coloring is based on the speed of the curve. This is a calculation I'm doing based on the tensor field, because from the tensor field we can compute the speed basically. And so when we plot a tensor field, it colors it by the speed automatically here. So you can see that that as the curve just goes in a circle, and then suddenly it like shoots out really fast. And so that's what's going on there. But what about in higher dimensions? So that was kind of like a tensor field in a one-dimensional line. But what if we construct some kind of product space type of thing? So we're gonna create the 60-point range from 0 to 2 pi again. And we're going to create a fundum called, which is a tensor field from the basically the direct sum of two of these guys. And what is this now? Now we can take a look at what's going on. This is just giving us basically this planar information that's a basis space of our geometry that we're going to pursue next in higher dimensions. Just like in one dimension, we had this one-dimensional, basis space. In higher dimensions, it gets more complicated, like this, basically. So, so what if we have a function such as wobble? And we're going to investigate some higher dimensional geometries here using this TensorField framework. So that's wobble. And what about wumble? So we're gonna need a bunch of like wobbles and wumbles in a moment. So we just have to set this up really quick so that we're all prepared. So we got the wobble, the wumble, and the wiggle is a little bit more complicated, but we can get this done as well. So it's a combination of the wumble plus the wobble times the cosine and then we have the wumble again and the wobble and we just have to set this up correctly so that we can proceed in a moment to do some further calculations. And that's just when you're doing the workflow in a session like this, you just have to type this out. So unless you've already copied and pasted it, but today we're gonna actually write this out. So now that's the wiggle, and now we can define an object based on the wiggle applied to the fundum. So what is this that we just made? Well, this is should we take a look? Well, we've got to fix that calculation in a moment. First, let's calculate some arrows. So these are a bunch of arrows. So in our object, we've got a bunch of basically coordinates that define our object. It's a parametric object. And now we've got arrows to go along with that object. And these are the normal arrows. And now we want to calculate the Gaussian curvature to help with our visualization. Okay. And now we should be able to visualize by now if we take the fiber of the object, which is basically from the wiggle calculation, and the fiber of the Gaussian curvature, and we do a mesh over that, we get the shape. So this is what the whole wiggle and wobble and wumble was about. So we're just defining a geometry here, and what's going on is the Gaussian curvature coloring just tells us that these different parts of the surface have different amounts of curvature going on, and you can see that it's stronger on the inside than on the outside. But so what we see here is that this Gauss tensor field, this is 60 by 60 basically tensor field, which for each coordinate it gives us the Gaussian curvature here. And this is a parametric surface, so we have like a fundamental domain, that a basis space from which we map onto this geometry here. And because we have something like that, we can define now a metric tensor across this entire geometry that's associated to this shape here. So we define surface metric of the object, basically. And what did we just define here? Well, this is basically a grid frame bundle, which is an outer morphism field on the manifold. And so this contains like a lot of information, actually, a lot of important information about the metric. So let's take a look at, a component in here. So at each point, 1.06, 1.7, for example, we have this outer morphism. So this is outer morphism. So this is a Grassmann outer morphism, and this is a non-diagonal metric tensor, basically. So we have all the components filled in here. So this is a two-dimensional geometry, actually. So for this shape in the fundamental domain, we just have basically a basis space of 2 dimensions. And so we can encode the geometry of this space using a 2-dimensional metric tensor, but this might not be a diagonal metric tensor. So at every point in the space, we have a non-diagonal metric tensor. Like if we look at another point, point 19, we can see the metric tensor is quite different in these two locations, actually. So it's 1.8, 1.9, that's pretty close, 0.3, 1.0, 11, and so there are some differences here. From point to point, the metric tensor is going to be different, and what the TensorField formalism has done now with Grassmann.jl, what I've implemented is you can do the full geometric algebra at every point in this tensor field with a fully general metric tensor, basically in any dimension, and it's the fully general thing that I'm interested in. And so now, what if we generate a basis for a local basis to study this geometry using the Grassmann metric tensor. Now we've got kind of this strange geometric product that it's when you do v1 times v2, you get 1 plus v1 2. And that's when it's 1 1 1 1. But we're actually dealing with a fully general metric tensor at every point with not just 1 1 1 1, but any values. And so what we're gonna do is we're gonna define a circle, and we're gonna use the same parameter t from before. So this is just a basic, circle shifted around. You can take a look at this circle. This is just a circle, centered at 2 2 here at the moment. And now what we're gonna do is we're gonna create another circle called circle 2, and it's a tensor field. And we're gonna take metric. We're gonna interpolate the metric with the circle, and then we're gonna take the fiber from the circle, and we're gonna make a new circle 2 from that. And that looks just like the same circle, but now this circle is in a non-Euclidean geometry. It's no longer in the base geometry, but it's in the geometry using the metric tensor, because what we've done is we interpolated this metric frame bundle basically on the circle. And this is just a really short command, like it doesn't seem like a lot happened here, but we're gonna see in a moment in the calculation what's going on here. And then we're gonna define another circle 3, and this is just simply when we take the object that we had before and interpolate it on the circle. So this is now let's look at circle 3. Now we see what's actually going on in the geometry is because we had this this shape here, and so we're now gonna put a circle on it. And when you map a circle onto the shape, it looks like this. And we can, but the problem is this is in 3 dimensions. This is using more degrees of freedom than is necessary. So circle 3 is kind of like doing more than is necessary compared to circle 2, which is a non-Euclidean circle, but it looks like a regular circle. But there's a metric tensor. And so now, what if we calculate the arc length of one of these circles? So you can see that the arc length of a circle does not follow a straight line, and that's because we were looking at this the circle that's going at the speed of it is changing. Like you see here, the color is brighter, so the speed of it was faster here. And so when we calculate the arc length along that, we can see that here that the arc length, shoots up faster during that segment, and it reaches, the value here. And now we can calculate the arc length along the same circle with the metric tensor encoded. So basically these two different tensor fields, circ2, circ3, they're not the same tensor field. And even but one of them is 2-dimensional and the other one is 3-dimensional. Circ3 is 3-dimensional, circ2 is 2-dimensional. But in the 2-dimensional one, we can still obtain the same characteristic arc length because of the metric tensor, basically. So that was, we computed this metric tensor for this geometry here, and we can put the circle on there. So there's the circle on there. So what about computing integrals? We can create this square domain here. And this is a product space. So this is my concept of product space, basically. So the squares just giving us, the x and y coordinates of a square, basically. So, and we can construct a disk as a tensor field using this square as a starting point. So let's do that. We've got now this disk thing. So what is that? So disk, this is just a kind of a simple thing to verify a numerical calculation. So we've got now this disk surface, which is just a circle, and the volume of this thing should be pi, basically. So let's calculate it. So if we integrate disk, we get the volume of it. And if we calculate the integral instead of integrate, we get the tensor field that represents the smooth integration. As we can see here, we integrate the circle, and when you go along the x or the y direction, the value approaches pi over here. And then once it's done integrating the circle, it stays at pi. That's why this is a flat over here, and this is flat down here because the integral is 0. So it's like an integral with compact support, and we can see what it looks like. And we can just ask for one of the components. Like if you just want to integrate in one direction, that's what it would look like, right? So that's how how you can compute some basic integrals, and this verifies the result, because it's pi. So let's just helps demonstrate some of those things. What about differential equations? So we have our initial condition, and we have our typical example of a differential equation system, the Lorentz attractor. And that has this following formula. Let's just get this correctly. Okay, that should be good. Now we can find a solution to this specification of a differential equation. Basically, this is a functional specification of the Lorentz system using some parameters. We've got my ODE solver, which I've been maintaining for quite a while, and we can get the results using this framework as well as TensorField framework. Oh, yeah, let's just put x0 there. We'll put 2 pi. And then this is, calculate until 2 pi the time. And then this is kind of the tolerance, 15, orders of magnitude. And then these are kind of this, I'm going to use the multi-step solver to solve this differential equation. So in my system, you can currently just use these different numbers that choose, whether it's a multi-step or single step or adaptive solver. I'm using the Adams-Bashforth fourth order multi-step here. And now we can look at the result. The result is a tensor field, basically. So let's take a look at it. And there we go. So that's the solution. And we can, try out different, things here. We can take a look at the tangent of that, if that interests us. Yeah, tangent, and yeah, we can just try out different things, So we've got this TensorField object with which we can, try out different things, and it supports all the geometric algebra that you want. So now let's take a look at some partial differential equations. Now I've got this I programmed this myself, this NACA airfoil generator thing. let's take a look at that one. So I'm gonna do a calculation on this geometry now. This is an airfoil geometry, and as you can see, this is American Clark Y airfoil specified with the NACA 4-digit code. And this is just pure type information, and whenever I want, I can generate the points associated to one of these, geometries. So this is where some of the MATLAB comes in handy, because I'm gonna just conveniently use this MATLAB DECSG command, which I'm feeding into that command to generate basically this geometry specification. And then I can generate a mesh geometry, and there are many different ways to get a mesh geometry. This is just a quick way to do it right now for this example, if you have MATLAB available on your system. And then using my geometry specification, it imports this into my Grassmann.jl TensorField framework. And what does this give us now? This gives us the point cloud P and the simplex manifold of triangles and edges. And now we can solve this. Well, actually, let's take a look at what this looks like. Let's look at the line segments. So this is the domain that I specified that we're going to be calculating on. It's a rectangle and the airfoil. And furthermore, we can visualize what all the triangles here look like, basically around the geometry here. So the triangles get a bit smaller as we approach there. And what else? So this is just a basic quick example, and then we can use this Poisson solver, for example. So what is this? This yeah. What P of t? This command here. This generates basically a simplex frame bundle, which is a fundamental aspect of what I'm working with. And there's two different syntaxes. You can do parentheses or bracket, and if you do bracket, you get something different. So this is actually really nifty, but I've demonstrated this before about 4 years ago. I've shown a syntax very similar to this. This is just a further evolution of that, what I did already 4 years ago. I just continued maintaining these capabilities and developing them further. And so this is giving me different things to work with in this geometry, basically. And if we actually want to solve a partial differential equation, so I don't have time to explain exactly how this specification works for the purpose of this video, but basically this is just your standard you know, differential equation solution. Nothing fancy at the moment. And this is for specifying the boundary values. So this is just these different values are for specifying the boundary values and the conditions of the Poisson equation. And because we have kind of this inflow at minus 1.49 where the mesh starts, that's why we have this boundary specification here. And anyway, if you apply this, you get the TensorField calculation result. And what is this? So this is the potential. So let's take a look at the gradient. So the gradient gives us basically the direction of the flow at each point. So what we can do is we can use that to plot basically the stream flow. So let's do that. Uh, 1.5. So we have to specify a region of the. Oops, did I spell that wrong? Stream plot. Okay. So there we go. So that's the flow around here, but if we zoom in, this doesn't give us nice enough detail, so we're actually going to modify these values a little bit. And there we go. Now we can get a better sense of how the flow is going around here. So furthermore, we can look at the Laplacian, and that gives us kind of a pressure perspective on this. And what I think is kind of interesting is to take a look at this right here, and this. First, let's zoom out. So we can get kind of interesting result analysis going on here, you know, just from these results using the tools available of differential geometry and whatever. Just so I could use the metric tensor to investigate this geometry now, or I could use all kinds of different tools to study these different geometries. Another thing that we can do is we can introduce further boundary conditions on something like this. So let's take the base of z. And we're gonna specify a little bit of a boundary condition here for transport diffusion. To get something a little bit more interesting going on. Oops. That's... Oh, we were missing something there. All right. So we're either gonna specify a this is the most complicated function that we need for, well, we'll see again, but this is, yeah. All right, let's see. Solve the transport diffusion. And we're just specifying there's another solution here. All right. Oh, of course, it helps to add the t there. All right. Now let's see what we've got. So now this is the transport diffusion. Let's actually correct this. I think we need 150 there. Huh? There we go. So we're just making sure that the result stabilizes. And so this is basically with the Galerkin least square stabilization. And so what's going on there is that based on the mesh size, there's a stabilization in the using the transport diffusion scheme. And at each point, there's a little bit of a diffusion that we can add based on the mesh size that helps stabilize the solution. And we can see that at the boundary especially. And what's going on here is there's heating going on the boundary of the airfoil there. And as the flow is flowing past. So we use the initialized flow from TensorField 1 that we computed using the Poisson calculation, the partial differential equation solution. And that was a tensor field, and using that we could feed the solution of that, the gradient of that, which is basically the velocity field. We could feed the velocity field into a transport diffusion problem where we introduce heating on the boundary of this here, and the heat flow is affected, by the velocity of the flow, and as you can see, the temperatures permeating in that direction. And if we actually take a look at there we go. We can see what's going on is that the heat is just smoothly going away from the airfoil where it's coming from, basically. So that's just some of the calculations we can take a look at here. So this is where all the heat buildup is occurring here, where the rate is increasing the most at the front. And then it's just kind of going from there, And let's also take a look at a hyperbolic differential equation. We'll just do this as well really quick. We're already taking quite a lot of time on all these calculations. And yeah, I just wanted to demonstrate some of the tensor fields. The point is that these tensor fields, they have geometric algebra entirely available in them. So let's do a calculation like this. So this is just another example to show what kind of calculations are possible with this isn't a very meaningful calculation. This is just a hyperbolic partial differential equation to demonstrate that using Julia, using Grassmann.jl, and using these tensor fields and using these different tools combined together, well, this is just this little function, so we don't need to so we just started a fresh new session right now. We just defined this one function and we're already up and running doing, simulations, partial differential equations, and so on. And this is all using Grassmann.jl as a foundation from the bottom up. So that's what's unique about what I've done is I haven't seen any other geometric algebra or engineering or computer algebra software out there which is entirely built up from the bottom up based on Grassmann algebra and geometric algebra, and also combining it with this TensorField formalism in this way that I'm using this kind of syntax I'm using right here, basically. So the results are, I haven't really had time to explain everything here, but basically, we have Cn is a tensor field. As the the final result object, and I can do geometric algebra on it. Like if I take the gradient on Cn, that gives me, the stream plot. Or let's look at the stream plot. Let's go from what is that, from negative 0.5 to 2.5, and negative 0.5 to 0.5. Let's look at the stream plot. So yeah, we can just analyze these different results, and I can superimpose, for example, that on there if I want to. So that's just all these different things you can do. There we can see that, all where the source is. It's from there. Yeah. So there we go. We've looked at a lot of different kind of TensorField type calculations, and from here on we can compute the metric tensor for this geometry, or go on into different kinds of calculations from here on further. I've also worked with the Wolfram language in the past as well. I've been at their Wolfram summer school, and I've worked there as a teaching assistant, and I mainly focus on this Julia language implementation at the moment because I'm very interested in the numerical computation capabilities, and the code generation for numerical computation in the Julia language was quite intriguing to me. And this is what it allowed me to come up with in terms of language design, in terms of coming up with a way of interacting with the Grassmann geometric algebra using computational language. And that's what this was about for me, so that I can intuitively play around with this algebra and do different kinds of things with it at a fairly good computation performance using my equipment at home here, researching mathematics. And that's just what it was about for me. So I am fundamentally an introvert, and I am basically writing this computational language design software open source on the internet because this is just what I'm doing as part of my introverted nature over a decade of being interested in mathematics. And I'm not doing this to particularly attract attention for doing this, although I would like people to recognize that I have been out here doing this for some time, that I have dived really deep into these concepts and done a pretty good job of implementing them in computational language. And I'm not doing that just to get get some kind of attention for it. But I do hope, I would like people to recognize in that space, in this space of computational language, that I'm here doing this thing, and that this is what I'm studying mathematics with. So this is just a little glimpse. There's a lot more interesting things I'd like to show that can be done with Grassmann.jl, but those things will have to be shown when the time is ready for that. And I'm going to return to my introverted studies of, researching different kinds of mathematics, not just geometric algebra. I am exploring many kinds of mathematics out here in the realm of numbers and different kinds of theorems. I am not just interested in geometric algebra by itself. I'm interested in applied mathematics and all kinds of other pure mathematics. And so this is just one aspect. I've released other packages in the Julia language, other software. I've done other things. I've researched other things. I've done things besides mathematics. I've been interested in music production and synthesizers, and I was interested in many different things. This was one of those things that interested me, and I happen to have done a really good job at it, that it resulted in useful software that, well, I think it's very useful, and I think there's some other people who would agree that this is an interesting, powerful way of algebra and computational mathematics.